Hi friends, torsional vibrations in ഒരുപാട് topics നമ്മൾ discuss ചെയ്തു. Now let us get into two sets of the next topics are there remaining. One is two rotor system and the three rotor system. ഏറ്റവും കൂടുതൽ ന്യൂമറിക്കൽസ് എക്സ്പെക്ട് ചെയ്യേണ്ട രണ്ട് സെക്ഷനാണിത്. Definitely there will be a 10 marks numerical question mandatorily the university will ask. So straight away let us get into the system. Now a shaft is connected, as you can see the figure, a shaft is connected. At the end of which two rotating discs which are known as rotors are connected, A and B. Now IA and IB represent what? The moment of inertia of rotor A and B. Now see, if in such a case when rotor A is rotating in one direction, let rotor A be rotating other direction. If both are rotating in different directions, then the shaft will experience a twisting vibration, twisting kind of torsional vibration. That is the torsional vibration occurring in the shaft. So at one point, see, if you rotate this in one direction and if you rotate this in another direction, now the twisting happens, and at one point there will be a necking region where the amplitude of vibration will be always zero, as we had discussed in the previous video. The amplitude of vibration will be zero. That particular point is known as the node point. So in this case, let us assume this to be our node point. Okay, and the area above the node point and below the node point, this line that indicates the amplitude of vibrations occurring in this section of the shaft. So based on the node point, we have divided the portion, the length of the shaft, into two portions, LA and LB, according to A and corresponding to B. So LA and LB, two portions of the shafts according to the node point. IA, IB, moment of inertia of A and B, rotor A and B. QA, QB, the torsional stiffness of portion corresponding to length LA, and QB, torsional stiffness of the portion of shaft corresponding to length LB. Next you have natural frequency of rotor A, FNA, natural frequency of rotor B, FNB. Now we have the general equation to find out the torsional stiffness. Q is equal to Gj by N. G is the rigidity modulus, J is the polar moment of inertia, which is pi by 32 into d raised to 4, where d should be the radius of the shaft. Generally, see, the question will be coming in different kinds of notations or different formats. Now we will see, this video will be divided into three sections. First section I will be explaining about two rotor system. Second section I will be explaining about a three rotor system, and finally we will discuss one numerical based on these two system. So you will understand clearly how to apply these theories. So generally the question may be asked to find out the node of vibration. Where will be the location of the node of vibration? So if node is asked, for a two rotor system, it is nothing but finding out the length LA as well as length LB. And secondly, you may be asked to find out what? The natural frequency of vibration. How to find out natural frequency of vibration. And one more thing might be asked. You will be asked to find out the amplitudes of, or ratio of amplitudes. Ratio of amplitudes will be asked, or else you will be asked to find out the amplitude of vibration of rotor A and the amplitude of vibration of rotor B. Okay. So general equation to find out the torsional stiffness is G into J by L. Now see, as there is no external excitation occurring in the system, we can write natural frequency of A can be equated to natural frequency of B, of rotor A can be equated to rotor B, because they are both connected to a single shaft having a single material. So the natural frequencies can be equated. Now what is this one? This one is 1 by 2 pi square root of QA by IA, and this is 1 by 2 pi square root of QB by IB. We have discussed all these parts previously also. The 1 by 2 pi will get cancelled. Remaining will be QA by IA, which is equal to QB by IB. Now we can substitute the value for Q from this general equation, and we can rewrite the equation as Gj, they will be constants, divided by L will be different, because this section is divided into two portions, LA and LB. So this will be LAL IA. This is equal to Gj divided by LB IB. So these much portions, the common terms can be cancelled out, and the remaining will be 1 by LAIA equal to 1 by LBIB. That means LAIA should be equal to LBIB. This is our first equation to calculate length LA and length LB. The moment of inertia I and IB will be given, or the data corresponding to moment of inertia of rotor A and rotor B will be given. From that we can directly calculate IA and IB from the data given in the question itself. You will be asked to find out LA and LB, as you will be asked to find out the location of node. So you have two unknowns and one single equation. So we need another equation, one more equation to solve this one, to find out LA and LB. That equation will be, see, the total length, let the total length of this shaft be equal to L. That means L can be written as what? LA plus LB. So here we have our second equation. So from both these equations we can find out what? LA and LB. See, while doing the numerical, the theory will be clear. See, certain data with respect to these equations will be given in your question. Okay. So we have found out the location of the node. Now to find out natural frequency, either you can find out natural frequency of A or B, because both are same. So natural frequency FNA can be written as 1 by 2 pi into square root of QA by IA. This can be again transformed into 1 by 2 pi square root of GJ divided by LAIA. This much hertz will be the natural frequency of vibration of the rotors. Now, lastly, you will be asked to find out the ratio of amplitudes. Now, ratio of amplitudes can be written as, if AA is the amplitude of rotor A and AB is the amplitude of rotor B, then the ratios will be directly proportional to what? LA by LB. Ratios of the portions of length corresponding to rotor A and portion of length corresponding to B. Now, either any one of the value of amplitudes will be given in the question. If not, it is alright to assume the value of amplitude A equal to 1 radians. Now here we are calculating all the amplitudes in radians. If it is asked in meters or such kind of units, you can convert the meters to radians using the equation. Now, so if nothing is given, you can always assume the ratio of the value of amplitude of A equal to 1 radian, substituting this one, and using this equation you can find out the second amplitude AB. So please pause the videos and look into the figure once again and try to understand the concept. Now the concept will be more practically clear when we discuss a numerical problem.